As an aside, with all of the integral techniques we've learned, we still have integrals that we would have a lot of trouble doing. This particular paper from 2010 is about the integral, I apologize because this is disgusting, h. The integral from 0 to 1 over the square root of 2, 4 root 2 parentheses 1 minus t to the fourth minus 8t cubed 1 plus t squared all over 1 minus t to the eighth. Now, I would not actually touch this with a 20-foot pole. 10 is too close anyway. But the question is, how do you do this? And this particular problem, this paper, addresses this in 4 different ways, 2 of which we know. It does it with partial fractions by attempting to factor that denominator into quadratics, which is ugly. And then it does it using trig substitutions. But then it does 2 other methods using complex numbers, which we're not going to touch. But this paper came out in 2010. It was followed in 2016 by 4 more different ways to do the same problem, and then followed by 2 more ways, and this one is weird. It even calls it an unorthodox approach. So in spite of the fact that we have a lot of different methods for solving a lot of different integrals, there's still a lot more out there. But that brings me to today's discussion on 7.6, 7.7, 7.8, and the exam review. What questions do you have for me? That did not work. Give me something better to focus on. There we are, focused. If you'll read it to me, yes.
The integral of x plus 2 e to the 2x plus 4 dx.
Like that? Okay. What do you think at first you want to do?
First thing I try to do is use up the 2x.
Okay. Then du is? But I'm not unhappy with this. I'm not. I like that. But what do I do with this part to go with it? Maybe. But if I were to think about that as my dv, then I want to think about integration by parts stuff, yes? And if I think about integration by parts stuff, then polynomial should be my choice of u before exponential, right? Logarithmic, inverse, polynomial, exponential. So if I were going to do that, I think I might make this the dv instead. But I want to stick with your choice of u at the moment. Let's see if we can make it work from there. Don? What did you see?
You can solve the u equation for x.
I can go you one better. Can't just solve it for x. I could actually solve it for x plus 2. If I divide this by 2, then 1/2 u is exactly x plus 2, isn't it? And now this integral becomes one-fourth the integral of u e to the u du. And that's integration by parts. So I was very happy that you saw that substitution. That works perfectly well. But now I got to do integration by parts. And then this is u and this is dv. If I had taken that top and solved it all the way to be x equals, then I put that in for the x, and doing the algebra I would need, I'd end up with exactly the same 1/2 u. Ta-da! U dv. Nope, it's a u. My u's get feet. The way I can tell them from my v's when I'm writing sloppily. More questions? Yes, there.
7-8, number 52.
7-8, number 52. Use the comparison theorem. So I want to try and figure out what to compare that function to. Okay, would you rather do 51 or 53? Okay, 53 says the integral from 0 to 1, secant x over x root x. And the problem with this integral is 0, right? That's my place where this function's undefined. Oh, it's secant squared x. Not that that saves me very much, but it is secant squared x. The graph of secant of x looks like this between minus pi over 2 and pi over 2. And this is a height of 1. Now pi over 2 is 1.57. I am. I didn't do 52 directly. I said I will do 53 or 51 instead. He picked 53. So I want to try and figure out if this converges or diverges. And it says use the convergence theorem, right? And since it says use the comparison theorem, I want to compare this to something. Well, let's just look at secant for a second. I know secant is always bigger than 1. Between 0 and 1, that's definitely true, right? And that means that secant squared is bigger than 1. And that means that secant squared x over x root x is bigger than or equal to 1 over x root x. Good so far? So instead of trying to do the integral of this thing, I'm going to try and do the integral of this thing. Now that's an improper integral, yes? Because it's undefined at 0. Gives me all sorts of haywire behavior at 0. So I need to do a limit to do this integral. With me so far? Because the comparison theorem says if f of x is less than g of x and both of them are positive, because that's definitely going to be bigger than or equal to 0, and the integral of g of x, f of x diverges, then the integral of g of x diverges. So I picked something smaller, that's my smaller thing, and I want to see if that blows up to infinity. If that blows up to infinity, it's going to take this one with it. And that's, since it said to use the comparison test, I need something to compare to. What's my thing to compare to? Usually a p integral. Integral involving just x to a power. So I tried to figure out a way to make it compare to an x to a power. By the way, if instead of having a lower bound for my function, I had an upper bound for my function, then I'd want to show that the top one converges. Because if the top one is a finite number, then it's got to hold the bottom one to be a finite number. If my big thing is finite, my small thing has to be finite with it. If my small thing blows up, then it's got to blow up the top one. So let's do this integral. First thing I do is I change my improper integral to a limit. And now, what's the antiderivative of x to the negative 3/2?
Minus 2 x to the minus 10.
Evaluated between t and 1, right? So I put in 1, wait a minute, negative 2, that square root goes in the bottom. I'm much happier looking at this as negative 2 over root x. When I put in 1, what do I get? Negative 2. Minus negative 2 over root t. What happens as t gets closer and closer and closer to 0 to this thing? It goes to infinity. And as a matter of fact, since it's minus a minus, that's going to go to plus infinity. Okay, wait a minute. My smaller integral goes to infinity. If this is infinity, the only thing this can be is infinity also. I need to try and make the function I'm looking at somehow not have any weird things in it other than powers of x. So you've got, I think in that one, inverse tangent? Okay, well, let's think about the inverse tangent. And are we going to infinity? Or are we going to 0? Where are we going with our inverse tangent? What happens if we go this way with the inverse tangent? I need a picture. In the back of the textbook, in the reference pages, are the graphs for the inverse tangent function. In those gray pages, gray edged pages at the back, there'll be some, they're in front of the blue edge pages, there'll be some pictures of the trig functions. And way down on the bottom of one of those pages is the graph of the inverse tangent. Looks like that, right? And that's got a horizontal asymptote. As we go off to infinity, I know that as x goes to infinity, tangent inverse of x is less than or equal to pi over 2. That's an upper bound. Here I used 1 because it was a lower bound, and I showed that the bottom went boom. If I have an upper bound, I'm going to try and show that the top gives me a number. And I agree with you. That is the hardest part about this, Jacob, is figuring out, wait a minute, what do I want to compare this to? That is not trivial. And that's why my default is to go back to something that's just in powers of x if I can figure out how to adjust everything else. We'll do a whole sort of heuristic analysis of this, the sort of hand-wavy thing where we go, well, this part isn't important, this part isn't important, this is the important crap. We'll do that more in chapter 11. It kind of relates to L'Hopital's rule. It kind of relates to something called big O order of a function, order of a function. And it has to do with growth rates as we go off to infinity. And that's specifically to this. So I got to go back and think L'Hopitalish. Leo, better?
Yeah.
Wonderful. Jack, you look like you have a question for me.
So whenever for 32, I'm just kind of confused on which one to actually use.
In that same section?
No, sorry. 7.6.
7.6, number 32. Secant squared, tangent squared, 9 minus that one?
Yeah.
Okay. I agree with you. I don't know which one to use either. Not at the start. Looking at this is nasty. But I do see two things that make me happy. I see secants and tangents in the same problem. And when I see secants and tangents in the same problem, I'm happy because I know those are related to each other. But I also see a secant squared. What's the relationship between tangent and secant squared? That's our Pythagorean thing, right? But there's another one. There's another relationship between tangent and secant squared. There's the Pythagorean one, but there's also the derivative one. The derivative of tangent is secant squared. So what if the first thing I do in this problem is a u sub? Then what happens? What does my problem become? But there's also that. right? Wait a minute. Wait a minute. There's a whole section of formulas involving square roots of a squared minus u squared, aren't there? Now I know which formula to go hunting for. I don't remember which one it is, but I know it's back there somewhere. I'm in the same boat here that I was with the first one on the review sheet that Maddie asked me about. I see that and I go, ew, wait, if I do this one sub first, then all of a sudden I see something I recognize. Or at least I think I recognize it. And you have that pattern right now?
It's already number 34 in the integral pattern.
So let's go back and see if number 34 fits. I jump back to my table, and integral formula number 34 says u squared over a squared minus u squared and a square root. That's perfect.
Why is it 44?
34 or 44? Which one did you say?
Oh, I provided the book, but I have a thing that's like, the 7th edition, so it's not good.
That's okay, but what's your formula?
The integral of u squared du over the square root of u squared minus a squared.
There's my problem. You said u squared minus a squared, and this is number minus u squared. It's the other order. And that's all right. The tables that are in the back of our book are actually on our Canvas page. I put them up there under Springer integral tables. I'm not sure if it's the 7th edition or the 8th edition, but last time I checked, these tables hadn't changed since the 2nd edition of this textbook. So we got a lot of stuff here, but those tables are actually the same almost always across. But that's an important thing to catch, Maddie. Knowing which order that denominator is in matters. Like it's the difference between if we were doing the trig sub by hand, using sine or using secant. And that's really what this is it's two chops of integration by parts with two trig substitutions. And that's why I don't want to do it by hand, and I'll look up the freaking formula. Better, Jack?
Yeah.
All right. Yes, ma'am. 24 in the same section. X cubed arc sine x squared. Ew. X cubed arc sine x squared. Oh. My first reaction is it's arc sine of ugly stuff. That should be my u substitution. If that's true, what's du? I don't have an x with my dx, do I? But I have 3 of them sitting out front. So let's take one, just like we did with the trig functions where we pulled one of them off when the power was odd. I'm going to take one of the x's here and put it back there. Now the only thing I'm missing is the 2. So I'm going to get a 1/2 with my du, right? 1/2 du is x dx. Now when you do the u substitution, what do you get? Is u inverse sine of u in my formulas in the back there? Why, yes, it is. But even if it wasn't, what would I do? I know how to do this problem. Inverse trig comes before polynomial. So I do u is the arcsine of u part, and dv is x, dx. So I can do this by parts, but the formula is back there. So, quick flip back to those gray pages, and I look for a formula with the inverse trig stuff, and a bunch of trig stuff is in a section labeled inverse trig starting around number 87. So, inverse trig forms. And I see u's with inverse sine right there, and inverse cosine, and inverse tangent. And then I see powers, so it's back here. Right, formula 93 is u to the n arcsine of u. So this thing would have to match a power of this, and if I do that, then the outside thing is 3/2 power. So doing this u substitution gets me out of that problem. Very well. Yes?
Look, anything like this you don't use now.
Only if I gave you the formula set. Or I said, I want you to do this integration by parts stuff. That's, psychotic. Yeah, this will be our integration by parts problem. Shoot me now. Oh, that's evil. And while I am evil, I'm a math teacher. It goes with the territory. I'm not that evil. Yana's like, sure. Talk to me. Number 8. E to the x over 4 minus e to the 2x. Okay. Again, I have to do a little bit of algebra playing here to see something nice. And my problem is this is an e to the x and this is an e to the 2x. If they were the same, I'd be in a better position. But they're different. Until I say to myself, wait a minute. That has a power that's really multiplication, 2 times x, right? So that means I can write multiplication of powers as a power of a power. So what if I write this as e to the x times 2, and then I write it as e to the x squared? What does that make my bottom? It makes it 4 minus thing squared. And what, then I'd have a u substitution sitting there going, aha, here I am. Tom, you had your hand up as well.
What?
Did you have your hand up as well?
Yeah, I was just like,
Oh, okay. Jack.
Section 7.7, number 34.
34. Figure out how far the runner went during those 5 seconds, right?
Yeah.
Okay, this time we've got a table. Which rule do we want to use? Okay, so that's the one with the delta x over 3, and then it's 1, 4, 2, 4, 2, 4, 2, all of those, right? Okay. x0, x1, x2, x3, x4, x5, x6, x7, x8, x9, x10. Good, there are 10. We have to have an even number for Simpson's rule, right? How far apart are my x's? that's delta x. And f of are these numbers right here. So when it says use f of x0, we're going to use 0. When it says you use 4 times f of x1, you do 4 times 4.67. And so all I have to do is put all the right coefficients in front of these numbers and add them up. That's the advantage. They gave me all the information after calculating. Better?
Yeah, I just was kind of.
But the whole point is that what we've got here is x's and f of x's. And realistically, this is a much better way of presenting the information rather than making you go through and figure out each of the numbers. I now know I've got 2 decimal places of significant digits. I'm going to keep 4 in my answer because that's 4 sig figs everywhere. I'm good. This or something else? Better, Jen? Okay, Maddie.
Can you go over 8 on review?
If you'll throw it at me, because I don't have my review sheet in front of me.
The integral of 4x squared plus x minus 8 over x cubed minus 3x squared minus 4x dx.
This is a partial fractions problem.
Oh, never mind.
The big part is going to be factoring the bottom, but everything there has an x, so I'll factor that x out, and then I get x squared minus 3x minus 4. Well, that's a quadratic that factors to be x minus 4, x plus 1. Oh, not only is this a partial fraction problem, it's a partial fraction problem with 3 fractions, each of which are simple, nothing repeats, nothing is quadratic. I like this one. It'll be A, B, and C, but I'll learn to live with that. A sneaky method. I'm going to have to do all that cross multiplying and gather my like terms and all that crap, right? And isn't that just thrilling? Bah. Let's do the cross multiplying. A, x minus 4, x plus 1. B, x, x plus 1. C, x, x minus 4. That'll be the top when I get a common denominator, right? So that piece has to be equal to this piece. Because I have no factors that are repeated, what would we normally do from here? We try and get 3 equations and 3 unknowns. Here is another method called the annihilator method. What are the roots of this polynomial? Well, there's 0 and 4 and -1, right? So I want you to plug in on both sides. I want you to plug in 0. I want you to plug in 4. I want you to plug in -1. If I plug in 0, then the left side is 0 plus 0 minus 8. What happens on the right side? That b term has a b times x in it, right? That whole thing is 0. This whole thing is 0. The only one that's not 0 is this one. And I get a times -4 times 1. So I get -8 is -4a. A is 2. No simultaneous equations required. when you plug in 4, well, on this side, you're going to get 4 times 4 squared, that's 64, plus 4 minus 8. And on this side, what's going to happen? This piece is going to become 0. This piece is going to become 0. The only piece that's not 0 is this one. So I get b times 4 times 5. So that's 60 equals 20b. B is 3. When you put in -1, 4 times 1 plus -1 plus -8. This piece becomes 0, because when I put -1 in here, I get a 0. This piece becomes 0. The only piece that doesn't is this one. The left side is -5. The right side is 5c. C equals -1. This only works when all of your denominators are linear and none of them repeat. You can always use the simultaneous equations. That works every time. This only works in some cases. But it happened to work in this one. Well, now I've got my partial fraction decomposition, right? 2 over x plus 3 over x minus 4 plus -1 over x plus 1. I know how to integrate those. For the record, I didn't learn that technique until I was teaching a course in differential equations 2 years ago. So I've gone through 40 years of being a math teacher without knowing that one. Boy, is it cool. Better.
18 on 706.
18 on 7/6. dx, 2x cubed minus 3x squared?
Yeah.
Since this is 7/6, this is our formula section, right? So my first reaction is that I should factor that bottom and write it like this. I'm pretty sure there's a set of formulas in the back that have like a plus bu in them. Aha! Starting around number 47, formulas involving a plus bu. Right? So I'm going to rewrite that fraction at the bottom there one more time. And instead of writing it as 2x minus 3, I'm going to write minus 3x plus 2. Now that looks like that a plus bu, only I'm using x instead of u, right? So now I look for a formula that's got an x squared and a plus bx on the bottom, starting in that section around 47. du over u squared plus a times a plus b, that's exactly it. There we go. And if I didn't have this formula in front of me, I'd be doing partial fractions right here. I don't know where your career path will take you in terms of what math you will actually be doing 10, 15, 20 years from now. Unless you're in a very small, specific set of careers. I don't expect you to be doing most of the integrals we're doing by hand. What I do expect is that you can then recognize, oh, the problem I'm working on looks like something I should be able to do an integral on. Set up that integral and then shove it in a computer or shove it into a table or shove it into something where I don't have to actually do all the calculus. But I have to be able to recognize it, set it up, and then understand the answer. At this point, though, the techniques themselves give me more insight into how the problems get set up. And the next 2 chapters that we're going to do are all applications for precisely that reason. That I can say, okay, here's a problem involving surface area. That's really an integral. How do we do it? Oh, I use this technique we already know. Off we go. I will tell you that one of my weirdest encounters in integrals came from a friend of mine who got her master's degree in long polymer chemistry. I have no idea what the hell she was doing. But she came out with this spectrographic chart, bunch of peaks and all that stuff, right? I know this much chemistry, people. I'm already in trouble. But they had to do something about the total molecular weight of this object, and they couldn't isolate it very well, so they couldn't get clean samples. They did the spectrographic analysis, and then she had to integrate that curve. There was no way she was doing that with a calculator. No way she was doing it because she didn't have a formula at all. All she had was the output. I kid you not, she printed the graph on filter paper. What's special about filter paper? Come on, lab science people. What's special about filter paper? It's got a known weight and a known density, grams per square centimeter, which you can then, when you filter something, you can weigh the whole thing with the paper and subtract the weight of the paper so you know how much precipitate you got. She cut out the graph and weighed it. She now knew how many square centimeters it was. She knew the area under the curve. There's a numerical method I never would have thought of, integrating by weight. It worked. This result is in her master's thesis. A little picture of her graph cut out sitting on a balance with a weight to 7 decimal places. I don't know what the hell she's doing with it, but it worked. I don't know what calculus problem you're going to have to solve, but there's a weird one. More questions on this stuff? Yes, ma'am.
If one of the entries like gives you a result of like something,
That's a reduction formula. The ones that I am most familiar with are the ones involving powers of x and trig functions. So there's a stretch back here where your integral formula, like integration by parts, gives you another integral at the end. Yeah, they want you to do that one. But some of these back here, powers of trig functions, and powers with trig functions. The whole idea is that you'll keep going until you're done with the integration part. Bleh. Which is why, you know, x to the fourth e to the x or x, those are long ass integrals. You got to do integration by parts 4 times. That's why we threw it in the computer the other day. Leo.
976, number 40.
7-6, number 40. So do a computer algebra version and then do it by tables. So the problem is the integral dx over e to the x, 3 e to the x plus 2. Well, that's disgusting. Go ahead, talk to me.
First, I decided to take the integral using the table, but it gave a number 50. That's on the computer. I took that one, the handout.
Okay, number 50.
That was the example I used.
Okay, but if in number 50, isn't that in terms of u? So what's your u substitution to get there from here?
I made my u like e to the x.
Aha. Well, then my du also has an e to the x. I don't have an e to the x next to my dx. So let's put one in by multiplying by 1. Now on the bottom, I have 2 of them, so I get u squared, 3u plus 2, 1 du. Okay, so 50 seems to be exactly the right thing, because that's a plus bu. I'm good with that. Now what?
I solved the integral using that thing, and I got my answer be eventually minus 1 over 2 e to the x plus 3 over 4 net plot and 2 plus 3 e to the x divided by e to the x plus constant.
Great. So I'm going to assume that's the right answer. Now you should take this same problem, the original one, go over to Wolfram Alpha or some other website.
Great calculator like this.
Careful.
It's like this.
Yes, you can use a TI Inspire on this because it's got a computer algebra system built into it. But that's why those, by the way, that's why those are not allowed on the exam. Because they'll do all the calculus we want to do all day long. But you could do it there. You can do it on on Wolfram Alpha. You can do it on Maple, Mathematica, Derive, any software package you'd like. Wolfram Alpha is probably the easiest one to get to nowadays. And make sure that their answer agrees with yours. Now that answer had logarithms in it, right? And that means that somewhere in your process, you might end up using the properties of logarithms to show that the 2 different versions of the answer are the same. So you may have to do some algebra to show that the answer you get from this formula is the same as the one you get from your Inspire. But that's exactly what I'm after.
If I get the same answer, when you say I got the same answer.
That's it. Make sure you wrote down the answer from the Inspire.
Or say for the one I saw, it was directly beside, so you know that's the one I did my hand at.
Well, I'm going to see you did number 50 with the tables, right? And then next week you'll say, when I did it on the Inspire, I got the same thing. Or when I did it in Wolfram Alpha, and then you can screenshot Wolfram Alpha and put the picture on your homework. As soon as class ends tomorrow, there will be 4 keys posted. 3 homework keys and the exam review sheet key will all be up at 1:51 when class ends tomorrow. Your homework will be graded tomorrow evening. I'll give it back to you at the start of the exam on Friday, but you'll have the keys to look at all that evening. And if you're going to the study session, which I heartily recommend, go talk to Mia and to Reese about all the questions you got. Tomorrow, we'll start doing some applications, so we'll be doing the same stuff. We'll just be using it. I will see you all then. Have a wonderful rest of your day.